Calculus today. Hi guys! Today, you will learn one of the best topics in calculus, which is continuity. This lesson is dedicated for the discussion of continuity of functions at a number, as well as to provide the definition of continuity, provide examples and applications in real life. This lesson also includes a brief review of what functions the limits are and a brief preview of discontinuity of functions. Why are we discussing about this topic? Well, it's pretty simple, because math is dripping with finesse and we all know that it is significant in our future lives. First, we will be having a quick review about what functions and limits are in order to understand the continuity of any function or limit at a certain point. A function is a rule that assigns to each element x from a set known as the domain and a single element y from a set known as the range. Consider the function y is equal to x squared plus 2. If we assign a value in x, we can get the value of y. If x is equal to 1, then y is equal to 3. If x is equal to 2, then y is equal to 6. And if x is equal to 3, then y is equal to 11. Using this function, we can generate a set of ordered pairs of x, y, including 1, 3, 2, 6, and 3, 11. And we can represent this function through a graph. By looking at the graph, each element x is assigned to a single value of y. If a rule assigned more than one value of y to a single element x, that rule could not be considered a function. As you may recall from pre-calculus, we can test for this property using the vertical line test. Any vertical line that would pass through only one point on the graph must assign only one value of y to each value of x for it to pass the vertical line test. Since we can draw a vertical line that passes through only one point on the graph, y is equal to x squared plus 2 can rightfully be considered a function. In this video, we will often give functions names such as f of x, g of x, and h of x. For example, when we say f of x is equal to x squared plus 2, we mean for f of x to refer to the rule that assigns the number y is equal to x squared plus 2 to any real number x. As we proceed, two types of functions to be aware of are polynomial functions and rational functions. Polynomial function is any function of the form of f of x where a sub 0, a sub 1, a sub 2 to a sub n are constants and n is a non-negative integer. N denotes the degree of the polynomial. You should be familiar with the common names of certain polynomial functions. A second-degree polynomial function is a quadratic function. A first-degree polynomial function is a linear function. And finally, a zero-degree polynomial function is simply a constant function. On the other hand, a rational function is a function r of the form r of x is equal to f of x over g of x, where f of x and g of x are both polynomial functions. For example, r of x is equal to x squared plus 2 over x cubed is a rational function. Note that we must exclude from the domain of r of x any value of x that would make the denominator g of x equal to 0, since this would make r of x undefined. Thus, x is equal to 0 is not included in the domain of the function. As we know, f is a function that can take an input x and transform it into an output f of x. Similarly, f can take the output of another function, such as g of x as its input, and transform that input into f of g of x. When two functions are combined so that the output of one function becomes the input for the other, the resulting combined function is called the composite function. The notation for the composite function f of g of x is f circle g of x. For example, if f of x is equal to 3x plus 4 and g of x is equal to 2x minus 7, then how could we find f of g of 2? The problem is asking us to find f of g of 2. One way is to work step by step with g and then with f. By substituting 2 to the function g of x, g of 2 is equal to negative 3. Now we use g of 2 is equal to negative 3 as the input for f. If we substitute negative 3 to g of x, f of negative 3 is equal to negative 5. Thus, f of g of x is equal to negative 5. A second way would be to solve for f of g of x directly. If we substitute the function g of x to the x of the function f of x, f of 2x minus 7 will be equal to 6x minus 17. Now, we can plug x is equal to 2 into the function. Therefore, f of g of 2 is equal to 6 times 2 minus 17, which is also equal to negative 5. Another type of function we'll be dealing in this video is the piecewise defined function. These functions are defined differently for different cases in their domain. For example, consider the following piecewise function. For x not equal to 3, f of x is defined by f of x is equal to x squared minus 9 over x minus 3. For x is equal to 3, f of x is defined by f of x is equal to 6. Let's proceed to limits. The concept of the limit is one of the most crucial things to understand in order to prepare for calculus. A limit is a number that the function approaches as the independent variable of the function approaches a given value. For example, given the function f of x is equal to 3x, you could say the limit of f of x as x approaches 2 is 6. Symbolically, this is written like this. But before we go deeper with our topic, what exactly is continuity? How can we say that the function is continuous at a point? Now, let's take a look at this graph. Here, we have 2 points, a hollow point and a shaded point. Shaded points are considered as points of continuity, while hollow points are considered as points of discontinuity. Let's make another example, but this time with 2 graphs. These graphs are different from each other. As you can see, this graph has hollow points or points of continuity, making it continuous at all points, while this graph is not continuous at this point because it has point of discontinuity. We can also determine if a function is continuous just by looking at the structure of its graph, or how you draw the graph of a function. This is an easier method in determining the continuity of a function. For instance, if you can draw the graph without lifting your hand, it means that it is continuous. But if you can't draw the graph without lifting your hand, it means that the graph is discontinuous at the point where you lifted your hand. Now, let's move to the definition of a function at a number. A function is continuous at the point if and only if it is satisfied these 3 conditions. First, f of c is defined, or the function of f of x is defined at c. Second, the limit of f of x as x approaches c exists. And last, f of c is equal to the limit of f of x as x approaches c. And now, to explain the conditions further, let's take the graph of f of x is equal to x plus 1 as an example. According to the first condition, f of c must be defined. And let's consider c is equal to 0. By substituting 0 to the function, f of c will be equal to 0 plus 1, which will be equal to 1. Therefore, f of c is defined and is equal to 1. The second condition states that the limit of f of x as x approaches c must exist. And by that, the limit of x plus 1 as x approaches 0 will be 0 plus 1 by substituting 0 for x approaches 0. Thus, the limit of x plus 1 as x approaches 0 is equal to 1. Thus, the limit exists. Thus, the limit of f of x as x approaches 0 exists. And for the last condition, f of c must be equal to the limit of f of x as x approaches c in order for the function to be continuous at 0. Recall that our f of c is equal to 1, and the limit of f of x as x approaches 0 is also equal to 1. Hence, 1 is equal to 1, and that the function is continuous at x is equal to 0, which can be seen as a shaded point in this graph. Now, let's try using these conditions to determine if the given function is continuous at a given point. Suppose that f of x is equal to x cubed minus x squared and minus 2, and that x is equal to 2. By the first condition, we must substitute 2 in the function. Therefore, f of 2 is equal to 2 cubed minus 2 squared minus 2, which will be equal to 8 minus 4 minus 2, and if simplified, will be equal to 0. Thus, the limit exists. For the second condition, the limit of x cubed minus x squared minus 2 as x approaches 2 must exist. The limit will then be equal to 2 cubed minus 2 squared minus 2, which is 0. Thus, the limit of x cubed minus x squared minus 2 exists. And for the last condition, f of x is equal to the limit of x cubed minus x squared minus 2 as x approaches 2. Hence, the function is continuous at x is equal to 2. Moving on to our next example, consider this piecewise function. F of x is 2x minus 6 all over x minus 3 when x is not equal to 3. And f of x is 2 when x is equal to 3. Thus, f of 3 is equal to 2 considering the second function of the piecewise. To solve for the limit of 2x minus 6 all over x minus 3, as x approaches 3, we need to simplify the limit, because if we simply substitute 2 to x, it will yield into undefined. Thus, we needed to simplify so that it will yield an answer of 2. By simplifying, x minus 3 will be cancelled. Then the limit of 2 as x approaches 3 will be equal to 2. Hence, f of 3 is equal to the limit of 2x minus 6 all over x minus 3 as x approaches 3. Where 2 is equal to 2. Therefore, we can conclude that the piecewise function is continuous at x is equal to 3. But what if we have a graph that is not continuous at a certain point? As you can see, this graph has a hole, making it discontinuous at that point. By using the conditions, we can prove that this is not continuous. At x is equal to 1, f of x is not defined. Therefore, f of x is not continuous. This is due to having a point of discontinuity or a hole at its graph. But we can make this function continuous at x is equal to 1 by having the hole be a shaded point. We can do this by adding a piecewise function of f of x. f of x is 1, where x is equal to 1, in order for the function to have a point at the point of discontinuity. And by checking, we can say that f of 1 is now defined. The function f of x satisfied the first condition. We can also say that the limit now exists, and that the both f of x and the limit of f of x as x approaches 1 is equal. Thus, the function is now continuous at x is equal to 1. In order to further understand continuity of a function at a point, we have here 4 different graphs. In this set, we need to identify whether the graph is continuous or not. The first graph has no holes and can be drawn without lifting this chalk. Thus, f of x is continuous at x is equal to a. The second graph can be drawn without lifting this chalk. Thus, the second graph is not continuous at x is equal to a. Therefore, this graph is discontinuous. The third graph contains a hole and a shaded point. But the graph can still be drawn without lifting this chalk. Hence, the graph is not continuous at x is equal to a. And therefore, this graph is also discontinuous. The last graph is considered to be continuous at x is equal to a, because it can be drawn without lifting this chalk. Therefore, the fourth graph and the first graph are the only graphs that are continuous at x is equal to a. Now, let's determine the continuity of these functions without graphing or without any aid from graphs. Consider the piecewise function f of x is x squared when x is less than or equal to 2, and 2x if x is greater than 2. Let's consider the first condition of continuity. F of 2, based from the first function of the piecewise, is equal to 2 squared or 4. For the second condition, the limit must first consider its left and right hand limits. We must first recall one-sided limits. One-sided limits state that the limit of f of x as x approaches a from the left must be equal to the limit of f of x as x approaches a from the right in order for the limit to exist. Going back, the limit of f of x as x approaches 2 from the left will be based from the first function and is equal to 4. While the limit of f of x as x approaches 2 from the right is based from the second function, which will also be equal to 4. And for the third condition, we can see that f of 2 is equal to the limit of f of x as x approaches 2. Four is equal to 4, therefore the piecewise function is continuous at x is equal to 2. Now let's take another example. Suppose we have f of x is equal to e raised to negative x squared. Now don't be intimidated by the letter e. We must first follow all the conditions. By the first condition, suppose that x is equal to 0, f of 0 is e raised to 0 by substituting 0 to x. Note that e is a constant that is equal to 2.718 and so on. And every number raised to 0 is always equal to 1. By the second condition, the limit of e raised to negative x squared as x approaches 0 is also equal to e raised to 0. By substituting 0 to x, we will have an answer of 1. Hence, the third condition is met, such that f of 0 is equal to the limit of e raised to negative x squared as x approaches 0, which is 1 is equal to 1. Therefore, the function is continuous at x is equal to 0. The concept of continuity can be also applied in real life. Let's consider UFOs and jets. Have you ever noticed that UFOs can be hanging around, checking out Earth for a minute, and then all of a sudden, the next instant, they're at the moon? I mean, what's going on there? If I take a look at their altitude as a function of time, they can be here checking out crops, and then boom, up on the moon, or perhaps fighting another UFO way up in the upper atmosphere. And then just for an instant, they leave the moon, come back down here and say, "Hey, are those crops still here?" and go back up to the moon that very instant. They're just jumping all over the place. Now, let's say that we have some jets, the Earth Defense Jets, whose sole job is to track these UFOs and to find out where they're going. Let's say when the UFOs are down here, checking out our crops and checking out Earth, our Earth Defense Jets take off and they get up to the altitude of the UFOs. Then all of a sudden, when the UFOs hop up to the moon, the Earth Defense Jets go. Well, where did you guys go? Or, oh, they're way up at the moon. So they slowly fly up to the moon. And then in that instant, when the UFO pops back down to Earth, The Earth defense jets sit there and go, "Where did they go? Ah, they're down there." But at the same instant, right after the UFOs pop down and see that the crops are there, they pop back up to the moon and the Earth defense jets go, "Okay, we're good, we can catch up here." But why is it that the Earth defense jets can follow the UFOs? Well, they can follow the UFOs exactly because the UFOs follow a discontinuous path. One instant they're down on Earth, checking out the crops, and then boom, they're up at the moon. They don't really have to travel between the two. They're just up there. The Earth defense jets don't have that ability. They can't just disappear one place and appear somewhere else. They follow a continuous path because they can't pop back down to follow the UFOs. So before we end our discussion, listen first to this song that will make you understand and remember the conditions for a function to be continuous.
Oh, the limit and depth of sea, they must exist. But there's one more thing that surely can't be missed. The limit of F as X approaches C. It better equal F of C for continuity. Oh, continuity. Oh, continuity. Continuity. Oh, to exist. The limit and depth of sea, they must exist. But there's one more thing that surely can't be missed. The limit of F as X approaches C. It better equal F of C for continuity. Oh, continuity.
We hope that you enjoyed and learned from our discussion. Thanks, guys!
For the limit and depth of sea, they must exist. But there's one more thing that surely can't be missed. The limit of F as X approaches.